There's a working engine on a silicon chip in Finland, smaller than a grain of sand, and it runs colder than deep space. Here's the problem it exists to solve. Quantum computers are fragile. To keep their qubits stable, you chill them to a hair above absolute zero, inside a refrigerator about the size of a chandelier. And then you have to reach into that cold to control the chip, which means running cables from room temperature all the way down. Every cable is expensive. Every cable drags heat down with it, and heat is exactly what destroys a qubit. So the more qubits you add, the more cables you add, and the more heat you're fighting. That's the wall. First come on what they actually built. A team at Aalto University in Finland, led by Academy Professor Mikko Muttinen, with Tuomas Uusnäki as first author, published this in Nature Communications. They took a transmon qubit, come with a standard building block inside most superconducting quantum computers, and ran it as the working fluid of an engine. An ordinary car engine runs what's called an Otto cycle: intake, compress, fire, exhaust. 4 strokes. This does the same 4 strokes, but instead of gas in a cylinder, the thing being squeezed and released is the energy gap of a single qubit. Second, the clever part. A normal engine needs a hot side and a cold side, 2 separate reservoirs. This one uses a single component, a quantum circuit refrigerator, that flips electrically in billionths of a second, heating the qubit one moment, cooling it the next. One part doing both jobs. That's what makes the whole thing small enough to sit on the chip itself. They measured it. It produced real work. Not just heat sloshing around the circuit, actual output. Third, the honest framing, because a lot of the headlines have been sloppy on this. This is not the first quantum heat engine ever built. Engines like it already exist using trapped ions, cold atomic gases, and flaws inside diamond. What's new is that this is the first cyclic one made from superconducting circuits, the exact same technology quantum computers themselves are built from. Which matters, because it means it can live on the same chip, made in the same fab, by the same process. Also, the efficiency is tiny, well under 1%. The researchers are upfront about that. What they did hit was better than a quarter of the theoretical ceiling for the setup they used, and their simulations suggest a tuned version should reach that ceiling. They call it a proof of concept, and that's exactly what it is. So what could it mean? The long-term goal is chips that handle their own heat and generate their own control signals locally, instead of importing everything down a forest of wires. Muttinen has pointed out that Finland's own roadmap calls for 1,000 logical qubits by 2035, which likely means hundreds of thousands of physical ones. Try that with today's approach, and the cabling alone becomes absurd. Absurd in cost, and absurd in noise. That's the real payoff here, not power generation. Plumbing. Quantum computers don't get useful until they get big, and they don't get big until somebody solves the wiring. This is a first crack at solving it from the inside out. Nothing about this changes your life this year. But the next time you hear that quantum machines are impossibly expensive to build, this is the kind of quiet fix that decides whether that stays true. If that made quantum computing feel less like magic and more like engineering, a like tells me to keep going, and subscribe if you want the next breakthrough explained the same way, without the hype.